Hi everyone. So it's just gonna be me today. We're just gonna do a short video going over a lot of modeling with two variables, and we're gonna talk about the line of best fit, and then the direction, the association, and the outliers and bounds of how you would analyze this kind of scatter plot, or when you're given a table of data. So let's start with an example while I explain these new concepts. So let's say that I have a chart of information telling me the number of hours, so hours studied, and a GPA. So like the average GPA compared to the amount studied in general. So we're given some information. I'm not gonna write anything specific because I don't have an exact graph, but let's say, so we would say our X value is hours, or units, it's hours, and then our Y value is GPA. So we'll make this like 1, 2, 3, 4. And this is a very simplified scatter plot. When you're given scatter plots, especially in your textbook from CPM, you'll find a lot more detailed examples. So let me just write some randomized information. And let's say okay. So let's say this is our scatter plot of information of according to how many hours you study, it's your GPA. So what is our line of best fit? Because that's our big question here. So line of best fit, there is a actual way to calculate this, of course, numerically, sorry. But in the case of when you're starting out and you don't have a calculator yet, you're not using any kind of like graphing utensils, the line of best fit is basically the average of all the information you have. And a kind of rule of thumb is normally when you graph your line of best fit, you want the same number of dots or points to be equal to the number of points on the bottom. So same number of points on the top is the same number of points on the bottom. So I would say line of best fit is about here, or let me do that, about here. So approximately we have 1, 2, 3, 4 dots here. You can count this as a 5, I guess. And then 1, 2, 3, and 4. So approximately this would be your line of best fit. And then, so now we're gonna look at association, outliers, and bounds. So, and direction. So direction for line of best fit just means, is the linear line, does it have a positive or negative slope? If it has a positive slope, in this case it does, we'll just say this is a positive slope. If it has a positive slope, then the direction is positive. If it has a negative slope, for example, we have another plot here, and the line of best fit goes like this, then we know that it is a negative direction. Association depends on the strength, or how many points is closer to that line of best fit. So for example, if I have a plot, similar plot to, I'll just make it the same example as the hours and GPA. If I have a line of best fit like this, and my information, my plot points are like all very close to the line of best fit, or relatively close to the line of best fit, we would say this has a strong association. So we refer to association as like strength, strong or weak. So this would be strong, and a plot like this, on the other hand, would be considered weak association. In other words, if you wanted to prove that, let's say again, so this is hours and GPA in just like an experimental sense. If you wanted to prove that the more hours you study, you get a better GPA, and you have your information when plotted looks like this, it would just mean that you have weak evidence. It's a weak association, so your evidence is weaker than if your plot looks something like this. Okay, and then outliers, we're actually going to use our first graph over here. So outliers just means that most of the points are near the line of best fit, except for maybe one or two exceptions. If there are more than like half exceptions, then we just know that the association is just pretty weak in general. But if there's one, or if there's two points that are like totally way out of bounds, totally like off the line of best fit, like the difference between the line of best fit and where that point is greater than any other, we call that an outlier. So in this case, this point would be an outlier, because if you look, all these points have a relatively small distance away from the line of best fit, except for this one, which has, I would say, more than triple the amount of the average length away from the line of best fit. So we would call this an outlier. In bounds, we would find using residuals. So residuals are the difference between a certain, so let's look at our third graph over here, and let's use something blue. So we look at the point that is the farthest away from the line of best fit from the bottom side. So it's from this side. Which point is the farthest away from the line of best fit? And we would say this one. This one is the farthest distance away from the line of best fit. So we would say, first of all, this distance is called the residual for the lower bounds. So there's more about this using graphing and LSRLs and stuff like that. But once you find your residual, if you use the same slope, let's say this line of best fit has a slope, m, remember, is our variable for slope, has a slope of 3, then this lower bound is also going to have a slope of 3. They are all going to be parallel, and the distance between is going to be our lower bounds. And the same thing for higher bounds. So we want to find the point farthest away, so we would say this point, farthest away, but above, this time, the line of best fit. And so this distance is the residual for the upper bounds. And same thing, we draw a line that has the same slope and is the same distance as this point is from the line of best fit. So m still equals 3, and we would call this the upper bounds. So some of you may be asking, why is this information important? Well, sorry, let me finish this. So when looking at or trying to prove something for association and causation, you need information to back you up. You need a plot, you need data. So, and if it turns out that, like, I'm trying to bring up a real life situation here. If you find out that your graph has a very, very weak association, has a very weak, that means you have very little evidence to prove your point. However, if you have data that has a very strong association and has a very small upper bound and lower bound, then you know that your information is accurate. You can prove it. Your conclusion has some sort of it has stuff to back it up. So a lot of this graphing can be used in real life situations. And another thing you're going to learn in your CPM textbooks is something called association and causation. So association, like we've talked about before, is how much your data actually fits your trend. So how much of it is accurate information? How much of it does it prove your point? And the stronger the association, so let's say, so like we said here, this has a, let's use yellow. This has a strong association and this is a weak association. The stronger the association is, the stronger their causation. So let's say an example from the CPM textbook is the more chess someone plays, the more likely, so like let's say a lot of members join the chess club, and then school brags that the Ivy League admittance rates is very high. So if your information from plotting this point of the number of students who were in the chess club versus the number of students who got into an Ivy League looked like the left graph over here, we know that your causation is very evident, it's very strong. And then however, if it's looks like something like the right graph, then we know that something like playing chess won't affect the Ivy League admittance rate. So there are things we'll go over like fake news article headlines to see if what's actually causation, and you're going to use things like your basic reasoning to kind of explain why these things work. Okay, and that's it for today.